Meta just removed the Prime Minister of India's post from Facebook. Not a random account, not a new page with 3 followers. The official account of Narendra Modi, one of the most visible political figures on the internet. The video was briefly unavailable in India. Then Meta restored it, apologized, and said it had been removed in error. Reports said the company blamed a technical glitch in its automated content filters. The Indian government was not satisfied and summoned Meta's public policy leadership for an explanation. That sounds like a filter saw something suspicious and pressed delete. But Facebook does not have one giant filter sitting behind the upload button. Behind every post is a distributed moderation pipeline that may examine the words, video frames, audio, links, account signals, location, and context, then decide what billions of users are allowed to see. Meta has not revealed which component failed here. It could have been an AI false positive, an incorrect policy rule, a legal request workflow, a bad rollout, or ordinary software executing the wrong action. So instead of pretending we know, let us design the system ourselves. How would you build an automated moderation platform for text, images, audio, and video across many languages without making every upload painfully slow? And when it makes a mistake, how do you discover which machine decided to silence a prime minister? Let us follow one post from the moment someone taps publish. The request first reaches an API gateway. It authenticates the user, applies rate limits, and creates a unique post ID. The video itself goes to object storage because routing a large file through normal application servers would waste memory and bandwidth. Now the post splits into 2 paths. The first is the fast path. This path checks whether the account is restricted, whether a link is known to be malicious, whether the post resembles obvious spam, and whether the media matches content already banned. That last check may use a fingerprint, a compact signature derived from an image or video. If the same prohibited file appears again, the platform does not need to understand it from scratch. But most posts are not exact duplicates, so the upload also enters a deeper asynchronous pipeline. The upload service publishes an event. Post created, video stored here, region, India, language, unknown, analysis required. That event fans out to multiple workers. One extracts the caption, another samples video frames, another uses OCR to read text inside those frames, another converts speech into text, others inspect links and generate embeddings, numerical representations of what the text, images, and audio appear to mean. This is where moderation becomes much harder than matching forbidden words. Imagine a frame showing a gun. The caption says, "Police seize these illegal weapons." Now take the same image and change the caption to, "Message me to buy one." The pixels are identical. The policy meaning is opposite. A model that sees only the image may remove a legitimate news report. A model that sees only the caption can be fooled. The system must understand the whole post. Meta has publicly described systems that combine text, images, URLs, and other signals into a shared representation. It has also described a multimodal few-shot learner that can compare posts against written policies and small numbers of examples across more than 100 languages. Why few-shot learning? Because abuse evolves faster than traditional model training. Imagine a scam appears this morning using a new phrase, a new logo, and a new payment link. A traditional workflow might require thousands of labeled examples, model retraining, testing, and a production deployment. By the time the classifier is ready, the attackers have changed the wording. A few-shot system can begin adapting from a policy description and only a small number of examples. It is not magic, but it reduces the delay between discovering a new abuse pattern and detecting it. Now our post has become a bundle of signals. Those signals go to specialist classifiers, spam, fraud, hate speech, graphic violence, adult content, terrorist propaganda, bullying, impersonation. Each classifier produces a score, not a final verdict. The violence model might return 0.08. The fraud model might return 0.03. The hate speech model might return 0.61. But those numbers cannot directly decide what happens. They go into a policy engine. This separation is critical. The model asks, what might this post contain? The policy engine asks, what should Facebook do about it? The answer can depend on severity, confidence, country, age group, and context. A news report showing violence may be allowed with a warning. The exact same footage posted to celebrate the violence may be removed. A simplified rule could say, if confidence in a severe violation is above 99.5% and no exception applies, remove it automatically. If confidence is between 70 and 99.5%, send it to human review. If confidence is lower, allow it, but keep listening for reports and new evidence. Those numbers are only examples. Real thresholds would differ by policy and action. Removing a post should require a different threshold from reducing its reach. Adding a warning should require a different threshold from disabling an account. So the decision router can choose between many actions. Allow the post, reduce its distribution, attach a warning, age restrict it, disable sharing, send it for human review, remove it, or escalate it to a specialist safety team. Meta has said it uses AI for three broad jobs: proactively detecting potential violations, automatically enforcing in high confidence cases, and prioritizing human review based on severity, likelihood of violation, and virality. Virality creates an interesting system design problem. If an ordinary post is incorrectly removed, a handful of people may notice. If the post belongs to a head of government, the mistake can affect public communication and become international news. You could add a high-impact account safeguard. Before automatically removing content from heads of government, emergency agencies or other critical accounts require a second independent model or urgent human review. But that creates another problem. Should powerful people receive protections? Ordinary users do not? A rule designed to prevent catastrophic mistakes can quietly create a two-tier moderation system. There is no purely technical answer. Now return to Meta's phrase, technical glitch. Where could the pipeline have failed? First, content understanding. A classifier may have seen a phrase, image, or slogan associated with violating material and ignored the wider context. Second, transcription, or OCR. Speech recognition may mishear mixed languages, names, slogans, or regional accents. Text appearing briefly inside the video may also be read incorrectly. Third, policy configuration. Models may have produced completely reasonable scores, but the system loaded the wrong regional rule or threshold. Fourth, a model rollout. Imagine a new classifier is released to 5% of traffic. Its scores are calibrated differently, but the policy engine still uses thresholds designed for the older version. Suddenly, legitimate posts begin crossing the removal threshold. Fifth, legal request routing. Reports about the Modi post said users saw a notice suggesting that the restriction was related to a legal request. Platforms need systems that can block content in one country while leaving it available elsewhere. A bad country mapping, incorrect content ID, or malformed request could restrict the wrong post. And sixth, the enforcement service itself. The AI may have recommended send to review, but a downstream service may have interpreted the action as remove. In distributed systems, the intelligent component is not always the guilty component. Sometimes the model is correct and an ordinary enum mapping ruins everything. This is why every moderation decision needs an audit ledger. The platform should preserve the post ID, extracted text, classifier scores, model versions, policy version, rules triggered, region, final action, timestamp, and whether a human or machine made the decision. Without that record, removed in error is not an explanation. It is only an admission. With an audit ledger, engineers can replay the exact decision. If the post is removed again under the same models, versions, and rules, the logic is reproducibly wrong. If it is not removed again, the cause may have been a temporary dependency failure, corrupted input, race condition, or partial rollout. Then comes the appeals system. An appeal should not send the post through the exact same pipeline again. Otherwise, the same machine reaches the same conclusion. It needs an independent path, another model, a human reviewer, or both. Successful appeals become valuable evaluation data, but they should not become instant training data. Reviewers can disagree. Policies can be subjective. Attackers can also abuse the appeal process. Instead, reverse decisions should be audited and used to evaluate new models. A new model can first be tested offline. Then it enters shadow mode. Finally, it reaches a small canary rollout. In shadow mode, the model makes predictions but cannot enforce them. Engineers compare its predictions against the live system and human reviewers. During a canary rollout, only a tiny fraction of traffic uses the new model. Monitoring watches for unexpected changes in removals, appeals, and reverse decisions. And that monitoring cannot look only at global averages. The entire system may appear healthy while incorrectly removing posts written in one language, originating from one country, or associated with one policy category. Metrics must be sliced by region, language, model version, rule, and enforcement action. The system also needs a kill switch. If false positives suddenly spike, operators should be able to disable automatic removal for that classifier and fall back to human review. They should not need to take down Facebook's entire posting system. Moderation becomes slower, but legitimate speech does not disappear because one model behaves badly. And here is the uncomfortable truth behind the entire system. Automated moderation has two kinds of failure. A false negative leaves harmful content online. A false positive deletes legitimate speech. Lower the removal threshold and you catch more harmful posts, but remove more innocent ones. Raise the threshold and you protect more legitimate speech, but allow more harmful material through. There is no perfect threshold. Meta acknowledged in 2025 that automated enforcement had produced too many mistakes. It said it would focus proactive systems more heavily on illegal and high-severity violations, rely more on user reports for some lower-severity cases, and use large language models as a second opinion before certain enforcement actions. Meta later said its enforcement mistakes in the United States had fallen by roughly 50% from late 2024 to early 2025. That suggests the future of moderation is not one super intelligent model judging every post. It is an ensemble of imperfect systems checking one another. A fast classifier catches obvious cases. A multimodal model evaluates context. A large language model provides a second opinion. A policy engine applies the current rules. A human handles ambiguity. And an appeal catches what all of them missed. Meta removed the Prime Minister of India's Facebook post, restored it, and said the removal was an error. We still do not know which component failed, but that uncertainty is the real lesson. At this scale, moderation is not simply an AI problem, it is a distributed systems problem, a machine learning problem, a policy problem, a monitoring problem, and ultimately a power problem. Because somewhere inside a data center, a collection of scores, thresholds, and service calls decides whether billions of people can see a message. Most of the time, nobody notices that system exists until it deletes the wrong post,